I am pleased to introduce Professor Chuji Wang, the Department of Physics and Astronomy at Mississippi State University, who will give this year's Friedlander Memorial Lecture. Professor Wang received his PhD in chemical physics from the University of Science and Technology of China in 1998. He then did postdoctoral work at the State University of New York in the College of Environmental Science and Forestry, and later at Mississippi State University. Following his postdoc, he worked at the Institute for Clean Energy Technology at MSU and then joined the faculty there in 2006. Professor Wang received the AAAR Benjamin Liu Award last year for his landmark work measuring the Raman spectra of single isolated aerosol particles. This work opens up a new frontier in aerosol measurement with the potential to radically advance our ability to characterize aerosol particle materials in situ. He holds 7 patents either granted or pending, has worked with small businesses to bring his technology to the market. He has authored over 133 articles, served as guest editor for AS&T and on numerous AAAR committees, and has advised at least 8 PhD students so far. I had the privilege of being a colleague of Professor Wang early in my own career and have maintained a close friendship and collaboration with him since. Please help me welcome today's plenary speaker, Chuji.
Could you plug in this one? I want to use this mic.
Okay.
Yeah. Thank you, Dr. Berg, for the kind introduction. Good morning, everyone. I'm so excited to be here with all of you in this beautiful and memorable place. This conference logo really catches the spirit. It reminds me of a couple of personal memories which I would like to share with you before we dive into science. I want to use the mic too.
What do you need?
So that one, just plug in the computer.
That's...
Okay, I can use this one.
What do you need, a laser pointer?
Yeah, laser pointer.
Do we have a laser pointer?
Cool. Okay.
I don't have the computer, it's all back there.
Okay. You just plug in this one, use my little computer. Oh, okay. So, laser.
Okay.
Yeah, got it. Sorry about that. Yeah, This photo was taken when I was doing my postdoc in Central New York, Syracuse, just a couple of hours away. That was where my family first arrived in the US and where my career truly began. This second visit was a part of a family road trip. We drove all the way from the deep south to Montreal, and this time from Canadian side. And on the way back, we dropped our daughter off at college. The parent that was bittersweet, proud moment. This would be my dream future visit coming with my motorhome. But I don't know whether we can park this in the waterfront or not. If someone did that, please let me know. By the way, this was created by AI. So, indeed, it's truly a great honor to be here to deliver this plenary lecture. I want to express my sincere gratitude to AAAR and the conference organizers for inviting me. And I also want to take this moment to acknowledge my research group, my collaborators, and the support from these funding agencies. They together made this possible. So here is the outline of my talk. I will begin with a brief view of particle levitation and optical trapping, and trace the evolution of optical trapping in aerosol science. Then I will spend a little more time on several case studies, highlighting recent advances in single particle studies using optical trapping. And I will close with some perspectives on future opportunities and the challenges in the field. We can achieve particle levitation using 3 methods in general. For example, we can use acoustic wave to levitate a particle, but this method is typically good for larger particles such as a millimeter in size. We can also levitate the particle using electrodynamic balance device called EDB. But in this case, we have to charge the particle, and the levitated particle exposed to electric field, which can be considered intrusive in some cases. We can also use optical force to levitate the particle. We call it optical trapping. Here, the trapped particle exposed to photons. Okay. So without further discussion about the advantages and the limitations of these three methods, I will focus only on optical trapping in this talk next. So this is the concept of optical trapping. There are two types of optical forces, radiation pressure force and photophoretic force, which are illustrated in this A and B respectively. Radiation pressure force is due to photon momentum transfer, which generates a scattering force in the forward direction, and a gradient force towards the highest light intensity spot, such as this focal point, and if laser is focused. Photophoretic force is due to photophoresis effect resulting from a temperature gradients or difference in thermal accommodation coefficient on the surface of the particle. So we can achieve optical trapping of nano to micro-sized particle in different media using radiation pressure force for light transparent materials such as droplets, glass spheres, or photophoretic force for light absorbing materials such as black columns, or both forces for materials in between. For majority of atmospheric aerosol particles, both forces play a role in the optical trapping. The idea of particle levitation using light force or optic force was first experimentally demonstrated by Arthur Ashkin in the early 1970s. Later, he introduced optical tweezers. This is probably the only case that one idea is really two Nobel Prizes, and both in physics but in different time. Stephen Chu used the idea to achieve the laser trapping and cooling atoms and received a Nobel Prize in 1997. Ashkin also won Nobel Prize for the optic tweezers and application to biological systems in 2018, 2 years before he died in 1908. AAR has a proud history of quickly adopting cutting-edge technology to advance our field. In 1987, I would guess many of us were not yet a part of this AAR community, me included. So, many of us may not know Ashkin delivered a plenary lecture that year at AAR on laser trapping and the manipulation of small dielectric particles and aerosols, just 1 year after optic tweezers were born. But during that time, there wasn't a single publication about optic tweezers and the aerosol studies. Over the following decades, enormous innovative applications were made in biology, which Ashkin later highlighted in his 2018 Nobel Prize lecture. The real beginning of optic trapping in aerosol science did not come until the early 2000s. For example, back in 2004, Jonathan Reed's group did carry out one of the first optic trapping studies in aerosols. And they demonstrated control and characterization of single aerosol droplets using optic tweezers. And they used cavity-enhanced Raman scattering to measure the droplet size and track the coagulation of two droplets. In the decade that followed, his group and a couple of others carried out numerous innovative studies on aerosol droplets, such as measuring single droplet extinction cross-section, hygroscopicity, and refractive index, starting phase transition, water on secondary organic aerosol aging processes, and so forth. Many of these were highlighted in the plenary lecture, starting aerosol processes, one particle at a time, by Jonathan Reed in 2013, which is about 12 years ago. So this is the second plenary lecture on a similar topic. This chart traces the evolution of optic trapping in our field and shows where we are today. If the early plenaries were considered versions 1 and 2, then today is version 3. moving from biology to primarily aerosol droplets to now any type of aerosols. So over the past decade, since the last plenary, single particle studies using optic trapping have touched almost all fundamental aspects of aerosol science. And this cartoon highlights the major but not exhaustive topics that have been studied during this period. So in a moment, I will present a few of them as examples. On the technology side, optic trapping systems have advanced significantly, no more limited to optic tweezers. One of the biggest advances is the development of the universal optic trap, we call it UOT. If you look at Atkins' optic tweezers, he used a single tightly focused laser beam to trap a spherical particle based on radiation pressure force. And here, the trapped particle is directly hit by trapping laser beam. So what is the universal optic trap? The universal optic trap is created by two counterpropagating focused hollow beams. And with small separation between these two foci, they form an empty optic cage where a particle is trapped. We call it a universal optic trap. So one key distinction is that in the universal optic trap, the trapping laser beams do not directly touch the trapped particle, which is very important in many situations. In addition, as its name suggests, universal optic trap can trap any type of particles, droplets, solids, spheric, irregular shaped, transparent, light-absorbing, chemical, biochemical, organic, inorganic, any type of particles in different media, such as air, liquid, and even plasma. And the universal optic trap has the highest trapping efficiency and best trapping stability, which is very important for instrumentation. As shown in these two movies, this trapping efficiency is nearly 100%, and the particle is dropped and trapped, and dropped, trapped. This is a single irregular-shaped carbon nanotube trapped for hours without noticeable motion. It's like sleeping rabbits here. So, the takeaway is this. Optic tweezers work mainly for homogeneous spheres and transparent particles based on radiation pressure force, but the universal optic trap is universally applicable to particles of any type in any experimental setting, and also trapping laser beams do not directly hit the trapped particle. So as a particle can be trapped for long periods, we can integrate other measurement techniques for the analysis and observation. For example, we can integrate light scattering, which includes Raman spectroscopy, elastic light scattering. This is for the characterization of chemical and biochemical property. And the elastic light scattering can measure the physical property, size, and morphology. And we can use cavity ring-down spectroscopy to measure single particle extinction. And we can use laser-induced breakdown spectroscopy to characterize the elemental composition. And other techniques can each be combined with optic trapping to study different aspects of aerosols. So next, I'm going to share some results from our recent single particle studies just using one of the combination. So optic trapping combined with the light scattering, which includes two parts. A is elastic light scattering, which is Raman spectroscopy, and the elastic light scattering. So this is a schematic of the optic trapping combined with Raman spectroscopy. Here we have a CW532 laser beam. It is used to form a universal optic trap in this airtight reaction chamber. A weak LED light illuminates the trapped particle for imaging. This camera monitors the size, morphology, and the stability of this trapped particle in real time. Raman signals are excited by scatter light from the optic trap. And this system is also equipped with relative humidity sensor, thermal sensor, gas flow control system, a UV light source, and a portion for the introduction of chemical reagents. So this is the actual system. Okay. So with these settings, let's jump into several case studies. So I won't go into much details, just highlight some unique capabilities of this technique and some key findings and the key takeaways in each of the cases. Okay. So first case is about interference of fluorescence in Raman spectral acquisition for bioaerosols. As we know, most bioaerosol particles or biomaterials produce fluorescence under light illumination. So here, we have a single bioaerosol particle trapped in this universal optic trap. As we can see, weak Raman bands are sitting on the top of a strong fluorescent background at the beginning of the observation. And after a short period here, about 10 seconds, fluorescence is gone. That is due to fast and effective fluorescent bleaching from this universal optic trap. So here we show the Raman spectra for 4 different pollens and the grass spores. They are fluorescence-free and well resolved, especially in this lower wave number region. So for comparison, this is the Raman spectra taken from individual pollens and the grass spores placed on the substrate using conventional Raman spectrometer. You can see here. And this is the Raman spectral method from individual pollen particles and the grass spores trapped in the electrodynamic balance device, even with laser bleaching, and many Raman bands are still buried under strong fluorescence. So contrast is clear with the universal optic trap, and the fluorescence is quickly and effectively bleached, making it especially useful for the study of bioaerosols. Let's look at 2 examples about single bioaerosol studies using this experimental system. So airborne particles, such as bioaerosols, pollens, fungi, and spores, interact with atmospheric traces and free radicals and water, driving complex biochemical processes in the atmosphere, such as formation of secondary organic aerosol and cloud condensation. Here, we investigate surface dynamics of single bioaerosol particle interacting with ozone. So here is a solid particle with gas first. Next will be solid particle with liquids. Okay. So here the Raman spectra from single fungal particles, 7 different types of fungal particles trapped in this universal optic trap exposed in air. Okay. These Raman spectra are very close, very similar, but slightly different because they are from similar bioaerosol groups. Okay. Then we introduce ozone to see how these fungal particles change. We take one of the 7 fungal particle example. This is the penicillin fungal particle. This figure shows time evolution of Raman spectra from this single penicillin fungal particle exposed to ozone for 40 minutes. As we can see, most Raman bands do not change over the 40 minutes, but 2 Raman bands marked by these red arrows, their Raman band intensity gradually increased over the 40 minutes. That is due to the lipid oxidation and formation of a palmitic acid as a result of a chemical reaction on the surface of the particle when exposed to ozone. This is the lower Raman shift region. In the longer Raman shift region, in the same case, as shown in these figures A and B, there is a huge Raman shift wave package where we mark 2 Raman bands on the left side and the right side, as they are from lipid and the protein of the particle respectively. As we can see, the Raman spectral features change over the 40 minutes. For example, the lipid Raman band became much weaker after 40 minutes. This figure C shows the ratio of these 2 Raman bands intensity, lipid and protein, as a function of time. In air, this ratio is almost constant, but in ozone, this ratio gradually decreases. And this result suggests lipid is more reactive to ozone than proteins. Okay. So let's look at the second example, single pollen particle interacting with water. Here, the solid particle with liquids. We are interested in particle growth and surface dynamics. And here, we trapped single subpollen particle in the universal optic trap. A subpollen particle, just one piece of pollen fragment from the pollen grains. So we gradually increase relative humidity in the surroundings. We see particle growth and water is coated on the surface of a single subpollen particle. Then we collect Raman spectra at a fixed relative humidity and look at the time resolution, time involvement. And for example, at this relative humidity 76%, as shown in fixed A and B, you can see water OH Raman band, lipid Raman band, and protein Raman band, their change of the intensity over time from first minutes to 20 minutes. Okay. So these real-time images track the particle sizes at the first minute, 20 minutes, with the increase of the relative humidity of water uptake by these pollen particles. So we see OH Raman band gradually increased over time. Meanwhile, liquid Raman bands changed very little, but the protein bands decreased in the first 5 to 6 minutes before reaching a steady state. So these results suggest that subpollen particle can absorb atmospheric water, act as cloud condensation nuclides, particularly in this high relative humidity. And also in this case, lipid is less responsive than protein to water. We also have investigated several different experimental situations. The detail can be seen in this recent publication. So these just 2 examples of bioaerosol studies. Next, let's switch to totally different type of particles, interplanetary dust particle, IDPs. So this is the tail of a comet. These are protoplanetary disks. They are full of IDPs because we want to know whether this technique would be useful for the study astrobiology, a search of life molecules in space, the interplanetary dust. So here we measured 4 different IDP simulants, Martian simulants, lunar simulants, volcanic ash, and Sahara sands. And these are SEM images showing their surface properties and morphologies. Their elemental composition are estimated using EDX spectra, energy dispersed X-ray spectra, mostly from carbon, silicon, and metal elements. This is a single particle Raman spectra from these 4 different dusts, and most Raman bands can be assigned to silicon-oxygen bond and oxygen with the metal elements. Next, we zoom in onto single dust particle. We use Martian simulants as example. We took a Raman spectra at the top, central, and the bottom. As we can see here, the Raman spectra at the top and the bottom clearly different, showing they have different chemical compositions at these 2 locations. This difference cannot be detected using any bulk measurement because they are surface specific. Okay. Even more intriguing, these 3 Raman bands 12, 13, 14 appeared at the top only. They are from CH stretch of organic molecules and the life molecules. Where do they come from? We have no idea. Possibly sample contamination or perhaps something that we do not yet understand. But this study demonstrates this technique could be potentially useful for planetary science and space exploration. The key takeaway is this. With single dust, we can learn things that bulk analysis completely misses. For planetary science, this is powerful. When you only have a handful of particles from Mars or the Moon or return to space mission, sometimes even 1 particle is enough. That is the power of single particle studies. So let's move to single particle reactor. I think this is even more convincing case showing the power of single particle studies. The heterogeneous chemistry of atmospheric aerosols involved complex, multi-phase, surface-specific processes. Traditional methods such as flow reactors, reaction vessels face challenges such as wall effects, surface modification, and size heterogeneity. Taking advantage of optic trapping, we can create single particle chemically defined and trap this particle in the universal optic trap and control the reactive environment. We term it the single particle reactor, SPR, to investigate heterogeneous reactions in single particle. So here we are interested in particulate bound mercury chemistry. Particulate bound mercury refers to mercury attached to airborne particles in the atmosphere, which plays a key role in global mercury cycling. Compared with gaseous phase aqueous phase mercury chemistry, particulate bound mercury chemistry is much less explored due to experimental difficulties. So here we create single particulate bound mercury particles using the base material single-wall carbon nanotube to mix with mercury compounds, mercury to halides, mercury to bromide, mercury to chlorides, then trap such a particle in the universal optical trap exposed to reactive gases, for example, ozone, to investigate chemical reactions. So first, we use SEM imaging to verify that these mercury compounds crystallized on the surface and in these single particles. So we use EDX spectra to analyze elemental composition. As you can see, these the bromine elements, mercury elements, they account for about 1%. That means the tiny mercury compounds attached to these single particles. Okay. This is the image of the trapped single particle where we marked 3 spots, A, B, C, on the surface of this single particle here. Okay. So this the Raman spectra collect individually from these 3 locations, A, B, C. And only location A has mercury compounds, as indicated by this fingerprint of mercury to bromide, Raman shift. That means this mercury compound is heterogeneously distributed on the surface of the particle. Then we look at the chemical reaction at this particular location A under controlled reactive environment. I'll show some results here. This is the time result of the Raman spectra taken at relative humidity 45%, ozone concentration 1000 ppm. We also investigate other set of experimental conditions. Here we have one Raman band gradually decreasing over the 10 minutes exposure. In the meantime, a new Raman band is emerging at this wave number. And we know this disappearing Raman band, as indicated by this arrow, is from precursor molecule, mercury to bromide. But we don't know this emerging Raman band. It is certainly from the chemical reaction product. So we proposed the reaction mechanisms as shown by R1 through R4. So basically, gaseous phase oxygen atoms react with solid state mercury to bromide to produce bromine atoms which are attached to carbon conjugated pi bond to form carbon bromine bond. So this is carbon bromine bond. Okay. These reactions last about 4 to 10 minutes, as indicated by the time rate of the Raman band intensity change. So this is the disappearing Raman band from mercury to bromide. And this is the formation of the reaction product. Similar reactions were also observed in other mercury halides. So here, HECl2, HGBrCl. Okay. Details can be seen in this recent publication. So this is observation of heterogeneous chemical reactions occurred at one spot on the surface of a single micro-sized particle levitated in the controlled reactive environment. So what I have shown you is just one example. This single particle reactor is a platform technology. Intuitively, by tailoring its chemical composition, we can create many different single particle reactors to study other heterogeneous reactions in single particles. So this study demonstrated that surface-specific chemical reaction can be revealed through single particle studies. So this is about the photochemistry of single particles. We investigate a photochemical reaction of C-spray aerosol containing this mercury 2 compound under the UV light radiation. Here we create C-spray aerosol droplet simulants. So we synthesize C-spray aerosol droplets containing these chemical compounds like mercury 2 chlorides, then trap such a droplet in the universal optical trap at varying humidity levels. Then we illuminate the particle using a UV light source containing these two different wavelengths. So this real-time image monitors the size of the droplet and the dynamics. This movie shows the droplet size increases with the increase of the relative humidity from 41% to 69%. This OH Raman band from water shows the change of the water content correspondingly, the different humidity levels. Then at a fixed relative humidity, we measure the Raman spectra at a different time. Okay? So for example, at relative humidity 40%, the time-resolved Raman spectra show a new Raman band after 12 minutes illumination. Here, this is from mercury 1 chloride. Okay. This Raman band tells us photoreduction reaction has occurred inside these single cis aerosol droplets, where mercury 2 was reduced to mercury 1. This is a photoreduction reaction. Okay? And this is a solid state and crystallized in the particle in the droplet and showing this Raman spectrum. This is very sensitive to humidity level. It's a fine balance between oxidation and reduction reactions. Detail can be seen in this recent publication. Okay. Well, this is just a few examples about single particle studies, all using one technique, optical trapping with Raman spectroscopy, and to characterize chemical and biochemical properties and their time evolution. Certainly, this is only one approach. Optical trapping can be also combined with other techniques for studying single aerosols. For example, pairing it with elastic light scattering, this second part of light scattering, allows us to characterize physical properties such as size, morphology, and even more. As shown here, we can levitate the particle here, and you can perform elastic light scattering in a full range of scattering angle. Instead of showing the characterization of physical properties, size, morphology using elastic light scattering, here I'm showing a different type of application using elastic light scattering. Very recently, we have investigated chiral particles using circular intensity differential scattering, CIDS, from optical trapped single particles. So CIDS is a light scattering technique. It's a normalized Muller matrix elements that can distinguish chiral particles containing molecules with helical structures such as RNA and DNA. So in this approach, we use left-hand and right-hand circular polarized light to illuminate the particle and compare their CIDS signals. Okay. So here are some experimental results. This is from silicon sphere. So as expected, CIDS signal from silicon sphere is essentially 0, and we measure 0.01 because they are non-biological materials. But for 3 different pollens and 2 amino acids, these bioparticles containing helical molecular structures, their CIDS signals are about 1 order of magnitude larger, with several distinct peaks at different scattering angles. So a lot of other detailed results can be seen this publication by Haifa. So this study suggests CIDS is a promising method to distinguish chiral particles from non-chiral particles or bio and non-bio airborne particles. Okay. We may use this technique to develop sensors for sensing. So one advantage of combining CIDS with optical trapping is that it allows us to take a repeated measurement on the same particle or single measurement that requires a long integration time when signal is weak. We have also investigated how particle orientation may affect CIDS signal, because some particle may exhibit morphological chirality. So to test this, we rotate the single trapped particle with 90-degree increments and take a repeated measurement and rotate another 90 degree and keep going here. So interestingly, for some bioparticles, their CIDS signal displays orientation dependence. And the detail can be seen in this recent publication. So far, I have covered several case studies, and which covers a wide range of single particles and several different topics, as shown by these check marks. These cases illustrate how optical trapping has enabled a wide range of single particle studies over the past decade. Although I have not touched on some other topics and other techniques combined with optical trapping, the impact of optical trapping on aerosol studies is conceivable, taking us much deeper in a truly microscopic level to uncover microphase chemistry from each individual particle, or secrets that are impossible to reveal with bulk measurement. So due to time limitation, I cannot include all of the recent studies here, but the greatest opportunity is still lying ahead. I want to pause it here. Use the next few minutes to share some perspective on the future. Okay. So I have 3 perspectives. First, we can integrate multiple measuring techniques into a single optical trapping system for multifunctional analysis, such as cavity Raman, Raman, elastic light scattering. This represents exciting future direction in the field. And in fact, some other groups have already begun to explore this. Here I have a couple of examples to show. So this is a combination of optical trapping with Raman spectroscopy to characterize the interplanetary dust particles, in which we used cavity Raman spectroscopy to measure single particle extinction, and we used cavity Raman spectroscopy to characterize their elemental chemical compositions of these 4 dusts. Okay. This is done by Haifa and this is the combination of cavity Raman spectroscopy with elastic light scattering to study single aerosol droplets by Jonathan Reyes and co-workers. So here, cavity Raman measures single droplet extinction. Elastic light scattering measures the scattering portion and determines the droplet size precisely. So in this way, both real part and the imaginary part of the complex reflective index can be retrieved. So this is the combination of Raman with LIPS to measure the single core particles. And here, both molecular components and elemental composition were measured in a single system. This was done by a Chinese research group recently. This just few case examples about this. So the second perspective, we will develop an array of optical trapping instruments, and each tailored for different purposes in aerosol studies. As we see here, some of them have been explored, some of them will be explored next. And this represents a huge challenge, but also tremendous opportunity, one that calls for collaboration among the scientists, engineers, small business, and research institutions. And in fact, some instrumentation and commercialization efforts have already begun. For example, this is platform optical tweezers commercially available from Thor Labs, which may be used for demonstration in classroom teaching of the concept of optical trapping. And this is optical tweezer 100 and built by this UK company. We have seen this a couple of times at the RRR conference. This is probably the only optical trapping instrument commercially available to date for aerosol studies. This instrument can measure particle size, refractive index, and collect Raman spectra from single particle. Okay. We are now collaborating with CloudSign, which is a small new company dedicated to atmospheric aerosol instrumentation, to develop single aerosol particle spectrometer. Okay? So in this system, we'll use a special sampling device that automatically draws airborne particles into the trapping system for measurement. Okay, here is Kai. He's testing this prototype outside our lab. This effort is currently supported by STTR Phase 1 project. I hope we'll have more results coming out soon. The third perspective that optical trapping will extend far beyond the disciplines that I've briefly touched here. One example is plasma, the fourth state of matter, in particular dusty plasma. Dusty plasma spans from fascinating natural phenomena such as comets, planetary rings, to semiconductor fabrication processes. They contain a lot of nano to micro-sized dust. Since plasma is an ionized gas, by definition, we may even think about this a kind of a plasma aerosol. Okay. So here, very recently we demonstrated we can not only trap single dust particle in the plasma, but also transport this trapped dust inside the plasma where we want. This allows us to use single plasma dust, micro-sized particle, as a non-intrusive in situ microprobe to study plasma fundamentals and plasma interacting with the dust. As shown here, this particle trapped in the upside electric field, this edge center. This movie shows the process. So here, this is showing the computer screen, the single dot here, and zoom in from this camera to the viewpoint. So this is a breakthrough in low temperature plasmas. And this is a very large magnetized dust plasma facility at Auburn University, where we set up a giant universal optic trap and successfully trapped a particle in this plasma. But notice, in this plasma environment, the acoustic levitation, electrodynamic balance device, even optic tweezer would not work. This is another unique capability of optic trapping. My student working on the optical alignment, she just passed her PhD defense last week. So this plasma trapping and the three perspectives that I want to share with you. So in conclusion, number one, from bulk to single particle, optic trapping enables us to uncover the microphase chemistry and time evolution from each individual particle that are invisible to bulk measurement. So number two, from conventional optic tweezers to now a universal optic trap, we can study any type of single particle in different environments. Number three, from droplets to dust, from Earth potentially to space, from atmospheric aerosols to plasma dust, or we may even call it plasma aerosols. Single particle studies using optic trapping have greatly expanded across the disciplines over the last decade, but are still in their early stages. The coming decade will bring both challenges and opportunities that I briefly mentioned early on. But the most important applications are still to come. So I hope many of you will be part of that. Thank you.
Thank you, Chuji. Do we have any questions? Yeah, Jonathan.
Thank you very much for your wonderful plenary, Chuji. It's great to see how you're pushing forward these universal optical traps and just the flexibility that you have with them. So congratulations on that. A senior colleague once said to me, particularly in the context of atmospheric aerosol, I look at pebbles, you look at boulders. And that's a question I've always battled with in thinking about the use of optical traps for particularly atmospheric aerosol. I mean, they have many broader uses. So I guess the question I'd like to ask is how far, where do you see the techniques going in terms of pushing us down really in particle size? And it's not about trapping so much as characterization, because you have so little material. And you highlighted combination of optical traps with mass spec. Is that something that you're pushing forward?
Thank you. That's a great question. As I list in the previous instrumentations, a combination of optic trapping with several different techniques. The last one I list, optic trapping with mass spectroscopy. That, so far, to my knowledge, I didn't see any single publication. I believe it could be attempted in the near future. But the difference, we have to use another way to charge the particle. I think it's possible. Yeah.
Do we have any other questions? Yeah, Rick.
Well, that was some very elegant works that you showed. You spent a lot of time talking about pollen. There's a puzzle in pollen that has attracted a lot of attention, and no one's been able to do anything directly probing it. And that is that pollen particles are so big, if you inhale them, they'll deposit in the upper airways. Yet they trigger deep lung responses like asthma. They do that through a process that involves high water activity, much higher than you probed in your experiments, that lead to the formation of a tubule that extends outside the parent particle, sometimes many, many tens of diameters, and that ultimately ruptures. The dynamics of that tubule growth and rupture in a particle that's not wet, that's at a water activity below 1, but is sufficiently high to get osmotic forces driving water into the particle and then providing the turgor to grow the tube. Ultimately, what that does is it spits out some cytoplasmic debris that includes allergens that now are small enough they can penetrate deep in the airways. What do you think about the feasibility of applying your technique to looking at this complex physicochemical dynamic that ultimately leads to a rupture and quantifying the kinetics and dynamics of that rupture event?
Yes, yeah, that's a great question. We realized even we just did a little bit pollen interacting with water and liquids, we realized very complex the process, and much more than we thought, like your comment. So, and we started with the subpollen particles, the very sensitive relative humidity levels. And also when we introduce ozones, they also have different reactions. Most of them are really surface dynamics. So that is a challenge, but I think this is a good tool to study that. So basically the whole pollen grains is not much meaningful. We are interested in subpollen particles because that can take waters and more reactive. And the surface dynamics are much more complex. Yeah.
And those subpollen particles have their own impacts even without looking at the reactions beyond, because they have impacts on the physiological system when they're inhaled.
Absolutely true. Yeah, like formation of a secondary organelle, so it's due to subpollen particle, which can size from 1,000 to 10,000 from single pollen grain. Yeah.
Looks like our timer's about to go off, so let's thank Chuji again.